Good afternoon. We resume our lecture on Six Sigma, and the topic that I'm going to be discussing today is a very key one in the process of achieving parts per million type of defects. This technique is called design of experiments, and it's, as I said, it's integral of the Six Sigma methodology. Let's take a look at why is it that we need to do experiments, and what is its role in the full range of quality engineering, which is actually today it has culminated into Six Sigma. That's the state where we are today. If you look at the picture today, you can see the clouds there, and underneath is weather. Then of course on this side we've got psychology, and I've got the economy here doing its ups and downs. On this continuum, if we come to the other extreme, you got this digital watch. If I may show you my digital watch, this is at the other extreme of this knowledge that is there. On one end, we've got very little knowledge about, say, something like the weather system. And on the other hand, when I talk about digital watches, we are right there. We know 100% about how a digital watch functions. In between are all the different systems that we have around us. Medicine, for example, chemistry, engineering, electronics, and so on. They're all over the place. They're on the spectrum. Now, what is the difference between systems on this side, which is to my left, and the systems which are to my right hand side? It turns out that man has always tried to control systems. Whatever we have around us, we've always made an effort to try to control it. And one of the things we have tried to do is to try to first do basic research. And of course, we began with observation, and then it seemed like some theory was behind it. Then we put in a lot of effort to try to understand the basic driving forces behind that process. In the process, we ended up with some fantastic theories. The result is something like the digital watch or the computer and the today's communication devices and so on. Their knowledge has progressed to the point we can write the exact equation how a digital watch functions, for example. This is not so if you look at the weather system. The weather system has too many variables. If you remember my cause and effect diagram, there are so many factors, there are multiple factors that affect the weather system, and it turns out that very little is really known how the weather system behaves. So we cannot certainly write down as of today's state of knowledge, we cannot write down exact equations to describe how temperature is going to vary, how humidity is going to vary, and so on and so forth. That we are not able to do today as far as weather systems are concerned. Same thing goes for psychology. We are not able to write down the equations. And also the same thing pretty well comes pretty close to economy. When it comes to talking about the economy, we know very little about the real process that is there. And of course, theories are there to try to sort of, and those are based on primarily observations. In between, of course, there are all these other systems, but we men and women, we can't really live with a system that is highly unpredictable, and we are at the mercy of clouds and sunshine and so on and so forth. We really can't do anything about them. We really can't live with a system like that. So there's been a constant effort to try to take systems which are on this slide, on the spectrum, and to try to gradually push them to the right hand side so we can control it. This has been our continuous quest. In fact, it began probably thousands of years ago. And today we have some knowledge in medicine. We have a fair amount of knowledge in chemistry. We have a lot of knowledge in engineering. And certainly in areas like electronics, we've really got all the equations known and determined and so on. So basic research and also applied research, it has advanced to the point on the right-hand side that we know everything about it and we can write down the equation. Now, if we are trying to, if our desire is to take systems that we know very little about and we want to push them to the right-hand side where we can control them, how do we go about doing it? Well, we can just stand around and observe. That's like one way. Just observe and try to see if there is any kind of correlation between what we see and what happens. Perhaps there is some driving, some cause and effect relationship. That's how perhaps these complex phenomena take place. For example, rain and so on and so forth. Then, of course, the process can be further modified, and this is where we have tried to use our intelligence. What we have said is, suppose we are able to identify some factors, and we are able to construct what we call the fishbone or the cause and effect diagram, and then we manipulate some of these factors and see the effect. So what we are really doing here is we are intervening. We are intervening into the process. We first try to figure out what are the different factors that might be affecting a particular process. Then we manipulate these factors in a manner that will produce hopefully some effect there. Now this is the experimental approach. This is the empirical approach. You manipulate some of the input conditions, you take a look at the output. If you can see some sort of dependency there, some sort of relationship, then of course you've got some clue as to how this process, this mysterious black box, how it operates. That's something that we can really figure out. In fact, this is what is done a lot. If you look at engineering, if you look at chemistry, if you look at a lot of these things, a lot of knowledge in this area has been basically acquired through empirical work, through experimental work. Now, if we did experimental work, that is just fine. But it turns out many factors are affected by multiple factors. Many systems are affected by multiple factors. That means somehow I have to basically take 4 or 5 factors and I have to manipulate them together in some complex way. This is not an easy task. It's not very easy to manipulate 4 or 5 factors together and then see the effect and then come back and say that the response, a particular response was due to factor A, another response was due to factor B, another response was due to factor C, and perhaps something was also going on in the background when factor D was active. This is not very easy to do if you just do one factor at a time trials. I'll show that later. I'll show why it is so difficult to do one factor at a time experiments and hope to see that you get an understanding of the process. So what we needed here was a technique that could take multiple factors together and give us a procedure, give us a methodology that could again give us insight as far as the factor effects were concerned, and indeed if there was any interaction between their effect, we should also be able to uncover that. This was done around World War II, and the gentleman who did this, his name is Ronald Fisher, Sir Ronald Fisher in UK. He basically came up with a scheme and he did some mathematical work also. And he was able to find a technique which is later on in mathematics it is called, in statistics it's called ANOVA, analysis of variance. This was the method by which you could find out which of these 4 factors really has an effect. Indeed, if 2 of those factors interact, if that is significant, this also you can find out. And also this led to slowly, gradually getting to an equation, an empirical equation form. Then of course other people got involved and they tried to evolve the basic understanding of processes later on as time went by. So this technique of manipulating multiple factors, this came from this professor, Ronald Fisher. We'll see how this was done. That's like the crux of it. So in fact, what we are talking about is we are talking about multiple factors manipulated together and some methodology that will let you see the effect of each of those factors and perhaps their interaction also. This is the sophisticated empirical approach. This is very different and much more advanced when you compare that to one factor at a time trials. It's quite different from that. Let's see how we get into this. If you look at any of today's systems, you don't have to really look at the digital watch. That's far too complicated. If you look at a factory, for example, or a machine, something that is doing grinding or something that is doing welding and so on and so forth. If you look at any of these systems, generally speaking, what you'll find, as you see on the slide, there are multiple factors that might be affecting the process. Some of these we call control variables, and these are of course on the input side. I've got raw material, I've got labor, I've got training level and so on and so forth. Then I've got process conditions, various process conditions which are there. These are going to be influenced by the control variables. These are going to be factors that might be impacting the process that is inside. In addition, of course, we've also got ambient temperature, vibration, humidity, and so on and so forth. These are external conditions, and these conditions are not necessarily always in our control. And somehow we have to run the process in the presence of all these noise factors. Anything that you're not controlling, we the professionals regard those as noise factors. So somehow what I have to do is I have to figure out what is going on inside this black box, which is the process. If I had the equation, of course, there will not be much difficulty in coming out and writing down the equation, the exact equation that will show the output as a function of the input factors. When that equation is not available, I basically have to do empirical work. And this is done a lot in R&D labs. In the R&D labs, they manipulate these different factors and they try to see what is the effect of it. Let's see how we do that. The beginning, of course, is again this fishbone diagram, where I've got some speculation about how a particular process works, and I've listed out the factors here. And the output is on the right hand side, which is the effect of all of this. Now, if I have to study this, if I have to study these different factors, I certainly need some special methodology. I cannot just do that the way ordinarily experiments are done. I cannot do that by manipulating one factor at a time. Just can't do that. I have to manipulate multiple factors together, because the real process has the involvement of all these different factors there. Therefore, what we have to do is we start with the cause and effect diagram, and then we come up with a procedure which will allow me to set the different settings, and these are called treatments, of these different factors which are there. Then look at the output and then do some special data analysis which will let me see whether factor A was important, it had an effect, a strong effect on the output, or B was important, or C was important, or D was important, or was there an interaction between A and B, or A and C, and so on and so forth. Now, the process, the experimental process involves all the factors together. I'm not doing a one factor at a time trial. That's not the way I can move from left to the right. I cannot go from the state of zero knowledge to perfect knowledge. I cannot do that by manipulating one factor at a time. Partly because factor effects, many times they interact. And that's a very complex phenomena. And that's why I've got to manipulate multiple factors together. And this is precisely what is done in DOE, design of experiments. It's this special method that Ronald Fisher came up with. So if you look at a process, I have process parameters inside, and I've got all these different factors, and I see this cause and effect dependency there. The effect is the output, and the causes are any of these factors which are to the left of this box there. And my goal is going to be to manipulate these factors in some systematic way so that I can work out the dependency of the output to these input conditions. This is basically what we are trying to do, what we'd like to be able to do. Now let me tell you, in a snapshot, let me tell you how this session is going to go and how the other sessions on design of experiments, how they are going to go. So you've got three factors. You have three factors, and notice a box there. Notice a box to the left. This is actually a 3D matrix. That's all it is. Now, when I'm speculating about the effect of A and the effect of B and the effect of C, what I do is I construct this matrix. This matrix is an arrangement that lets me manipulate simultaneously all three factors in a particular way, in a special way. And let me actually show you. Let me show you how this manipulation is done. We will assume for a minute that factor A has two alternative positions. Factor A can be set at low level, and also it can be set at a high level. So in fact, factor A has only two levels. For simplicity, I'm assuming that. Factor B also, let's say, has two levels, low and high. Factor C also has two levels, low and high. If I combine 2 times 2 times 2, I've got 8 combinations. So there are 8 different ways in which I can run this process when I'm manipulating these factors A, B, and C. Each can be set at two levels. Each can be set at two levels. What I'm really trying now is, I'm trying to sort of see, can I combine 2 and then 2 and then 2? Can I combine them? And that combination is done by this special matrix there. And I'm going to tell you a lot more about these matrices. These are called DOE matrices. These are special factor manipulation plans. These are special plans that allow you, that really enable you to conduct these different experiments by appropriately adjusting the different treatments that this process is subjected to. Okay, what is the effect of all this? In between, you see that fat arrow there. That's where the data comes out. I run each of these experiments. So for example, this experiment here will be run at the setting of A at high, setting of B at low, and setting of C also at low. So I've got high, low, low. That is going to be the setting for this experiment. It will have three factors set at high, low, low level. When I conduct the experiment, when I run the process by holding A at high, B at low, and C at low, I get some response. I record that response. That's like one of the outputs from my first round of experiment. My second round could be this one, when I've got A at high level, B at high level, and also C at high level. So the setting for this experiment, setting for running this experiment is going to be high, high, high. I do the same thing for each of these corners there, and therefore I end up running 8 different rounds of the experiments. I have now run, because of this scheme there, because of this matrix scheme there, I've run 8 experiments. So the data that I have now on this big fat arrow there, this data now has the results of 8 experiments. Then there is a data analysis procedure. I apply some data analysis procedure to the data that comes out, and the result of that is going to be, I'll be able to calculate actually main effects. These are going to be the single factor effect. Effect of factor A, effect of factor B, effect of factor C. This I'll be able to find out individually. Even if I've run the 8 experiments by manipulating all 3 factors together, the data analysis procedure is so good that it gives me separately the effect of A, the effect of B, the effect of C. That I'm able to see. These individual factor effects, these are called the main effects. Now, of course, there are other complications. The effect of factor A and factor B, they may interact. This also you can find out from the same data. The data that you have there from the 8 trials, you will be able to find 2-factor interactions and perhaps even 3-factor interaction, because I've got A, B and C, 3 factors. They may interact in a complex way. That also I'll be able to uncover by doing this special data analysis technique. So in fact, the reason is these plans are special plans. These plans are actually very special plans. The scheme is a very special scheme. That scheme is unique, and that will allow me to separate out the effect of A, effect of B and effect of C, and also the interaction of the 2-factor interactions, also 1 3-factor interaction, because there are 3 factors. There will be 1. In fact, it will be just a setting of certain values of A and B and C, and I'll be able to see the interaction effect of all 3 working together. Now, of course, there is some other line written there. Notice here, I've got a statement there called significance. I've got a phrase there called significance. I've got main effects, interaction, and significance. Significance is a statistical significance. It's a statistical term that actually says the effects that I notice, they are going to be significant. They're going to be audible in the background of noise. It's sort of like this. Let's say if this studio had it had a noisy fan running, and I was trying to do my lecturing in the presence of that noisy fan or the blower that was there. And I can simulate that by saying somehow I raise the noise level, and either I can raise the noise level and let you see what happens, or I could reduce my voice to the extent that it becomes almost indistinguishable to the background noise that is there. And let me just try that. So if you notice now, my voice got lost. The effect of my voice cord and breathing and everything, it got lost in the background of noise. In fact, if someone was sitting next to me, even next to me, he would have a pretty tough time to find out what I was saying. When I talk about factor effects, each of these factor effects are significant relative to noise, relative to background noise, because that background noise will be there. But what statisticians have done it, they do not say that the effect is significant unless it's like a multiple, significantly higher than whatever that background level of noise is. That's actually how they figure out whether the effect is significant. I need to worry about it, or I can just let it go without doing anything. Now, after I've got these effects calculated, I can do some plotting. And notice here I've got the effect of A plotted out. This is like when A goes from low to high setting, this is what happens to the response. The response goes up. When I move the setting of B from low to high, the response comes down. And when I manipulate C from low to high, again the response comes down. Out of these factors A, B and C, you can clearly see that C has the largest effect, C has the strongest effect. And if my goal was to try to maximize response, I would have set A at high level, B at low level and C at low level. If I would pick this setting for A and this setting for B and this setting for C, the combined effect hopefully is going to be the maximum value for the response. Okay, that's like an empirical optimization. That manipulation actually has been taking place empirically. What else can I do with the data that I have there? There are techniques available with the help of which I can take the data that came out of that green fat arrow. I can take the data and I can come back with an equation. And look at the equation there. Y is the response. I've got alpha plus beta times x1 plus chi times x2 plus delta times x1, x2 and so on. So this is now a mathematical model, and I can construct this model by regression analysis using the same data that I've got over here. I can use the same data, I can bring it through, and I can do multiple regression, and I can find out this equation. I can find this equation. Now, because this equation has been derived using empirical work, we call this an empirical model. What is the use of this empirical model? Remember, the ultimate goal is for us to get in there and to make everything controllable like the digital watch. Now, fortunately for the digital watch, we did not have to conduct experiments. Here we could study Ohm's law, Kirchhoff's law and many other things that was provided to us by people from physics, the PhDs from physics. They gave us the equations. They gave us those electronic equations and so on and so forth, and we were able to design this watch based on those equations. In this instance, when I'm trying to manipulate factors empirically, I do not have those equations, but I can come up with a proxy equation. And that proxy equation is this regression equation, which you see at the bottom of the slide here. Y equal to alpha plus beta times x1 plus chi times x2 plus delta times this thing. This equation is the empirical equation. This empirical equation is almost as good as that original theoretical equation if one was able to construct it. What is the use of this? Well, I could go to the next step. I can optimize this function. I can find the values of x1, x2 and so on and so forth that will maximize y or minimize y, whatever be the desire. That optimization I can now do using this empirical equation. So just see where we started from and where we are. We started with a cause and effect diagram, which is like this one. And I conceptualized them, I identified some of the factors, and I used them in my experiments. And I constructed this matrix. This is a special matrix. And after I ran the experiments, collected the data, figured out the main effects and the interaction effects, constructed the regression model, and then of course I could apply optimization. Now what do you do? What do you really try to optimize? Well, if it's like a production system, I may try to maximize productivity. If it's a scheduling system, I may try to minimize the time to finish all the jobs. If it's a chemical process, I may try to maximize the utilization of raw materials. I may try to maximize the utilization of anything else that is there. Or I may try to maximize yield. These things are possible when I apply optimization. And this is quite easy when you've got an equation in front of you. Whether it's based on basic theory or it's derived by empirical work like we've done here. In a lot of work in Six Sigma, we would be forced to derive actually these or construct these empirical models. And therefore, Six Sigma experiments also are going to be special experiments. They are all going to be guided by DOE, the general principle of DOE. What is the effort? What is actually the aim of Six Sigma? Six Sigma tries to reduce variation in quality. If you've got any kind of variation in quality, for example, if you look at the output of this process here, the output is highly variable and this may not be satisfactory for a customer. What we would like to do is we'd like to make this process as tight as we can make them. And once we make the process tight, it's going to satisfy the maximum number of customers. So our goal is going to be then to try to shrink the spread of the process. And I'll show you later how we end up doing that. This is to be done by us. We are the specialists. We are going to be conducting some experiments. And if you follow the DMAC procedure of Six Sigma, define, measure, analyze, improve, and control. If you follow this 5-step procedure, at the improved stage, we are actually using DOE. And that's when we are trying to manipulate the different variables, find the effects, and also optimize the process. All those things could be done with the sole goal to try to minimize variation in the process, in the output of the process. That's like one goal. Also, in the process, we'll end up reducing defect. That's like also another objective of conducting experiments. There are many techniques available, of course, many statistical techniques available, and you've already seen histograms, Pareto charts, fishbone diagrams, you've seen tabulation of data, you've seen run charts, scatter plots, flow charts. These are techniques that almost anyone can use. In fact, the workforce should be trained on these techniques for sure. Then, of course, the engineering types or the production supervisors, they should be able to control the process online, and they can use control charts. So training also should be provided at this level so that they can manipulate control charts. They can actually use the control chart to try to locate any kind of defect that is there for which there is an assignable cause. Then of course we've got these techniques, and these are the most advanced statistical techniques. These are part and parcel of Six Sigma black belt training. And the black belt people, they can teach this to others also. What are the techniques involved here? We already heard about DOE. We also heard about regression models. So there are certain other things called significance tests and confidence intervals. These are advanced techniques which are all used if you are trying to optimize the process. And Six Sigma uses this, the top of the pyramid. Six Sigma very heavily uses these techniques in trying to do it. So every black belt should know techniques from top to bottom. Every black belt should really know all the techniques that are there, and especially they should really be focusing on this, and they should be able to help other people who are trying to use DOE or regression. What exactly is an experiment? I gave you an overview. Now what exactly is an experiment? Is the process of systematically varying the variables of interest. These are the control factors about which you've got some speculation. And the idea is to try to make sure you are able to see the effect. And you are able to do this by manipulating some of the input conditions and by observing the output. That's an experiment. We do experiments all the time. In fact, it's surprising how often we are conducting experiments and we are not very mindful of it. We are actually indeed, we learn so many things by doing hit and trial. That's also an experiment. We make some change in the input, we change the input and we look at the output. And we try to see, is there a dependency there? If there is something, then we learn something. We find out how this particular system works. Every time we are doing a trial, we are measuring the response. Every time we are doing a trial in an experiment, we are measuring the response. And some of the critical concepts which are involved in an experiment are variables are manipulated by the experimenter. Random assignments of experimental units are there. Many times what happens is, let's say you're conducting an experiment and you did some of the experiments early in the morning when temperature was low and the sun was not there. Then you conducted some other experiments at lunchtime when temperature was high and the sun was out and the sun was pretty bright and so on. And then you conduct the same kind of experiments you again conduct in the evening. Now you are manipulating only the variables in which you are interested. So you went to your fishbone diagram and you picked up your control variables from there, and those are the ones you manipulate using the matrix that is there. Unfortunately, while you are doing this, sun is also doing its own thing. So it was cool in the morning, it became warm, then perhaps it cooled down again. That also might have an effect on the experiment. Therefore, what you have to do is you have to randomize the order in which you run your trials. This tends to fool factors like sunshine and so on. You'll end up finding some effect of that, but it will get randomized, and therefore on the average those things are going to cancel out. And this I'm going to discuss again. As we get deeper into this, we're going to be doing this. And something else we should also try to do, and this is kind of somewhat of an advanced concept, we should try to avoid confounding of variables. That means in places where manipulating one particular variable, another factor should not be confounding the same effect. It should not actually be such that I'm trying, for example, to find the effect of one factor. Let's say that's my left hand. And I'm trying to do something with my left hand. At the same time, I should not also bring my right hand and try to do this. Because then when the effect takes place, I would not know, is it due to my left hand or is it due to my right hand? Here, the effect of my left hand and my right hand, they are confounded. This makes it very difficult to figure out which factor actually, was it my left hand or the right hand that produced the effect. The same idea we use also when we are designing experiments. We try to avoid confounding. We let the variable stand on its own. Whenever we do settings of an experiment, we make sure if you're manipulating a particular variable in a certain order, there should not be another factor that is also manipulating in the same order. If we did that, if we did, for example, temperature high and low, and also at the same setting we did pressure high and low simultaneously, and we did not run any other trial, it will be very difficult to figure out what the effect that is observed. Is that due to the effect of temperature, or is it the effect due to pressure? Is the effect due to pressure? Now, if you conduct some experiments, And some very simple ones, of course, are there. For example, this is, of course, not an experiment, but you pretend that some factor is being manipulated and you're looking at the response. So, for example, number of packs of cigarette smoke per day. So, half a pack or 1 pack per day, 1.5 packs per day, 2 packs per day, 2.5 packs per day. Now, something that is really correlated, it's well established in medicine, is the severity of cancer. Severity of people having cancer on some scale. That's got a correlation with the number of packs of cigarette smoked. You see that rising trend there? That rising trend actually says that there is a relationship between, there is a dependency between number of packs of cigarette smoked per day and the severity of cancer that the person contracts. So this is actually something fairly simple and easy to see when I've got only one factor. Notice something else. There are these, this is not quite a straight curve. This is not quite a straight line or a smooth curve. There are some fluctuations. There are some random variations there. And that is because at some point in time, the total effect of causing cancer, that's not the effect of smoking only. It's got genetic orientation and a lot of other factors which are there that may differ from people to people. It may differ from city to city or situation to situation. Those also have their effect, and they also actually make people cancer prone. Let's see, if you're living next to a refinery and the refinery is spewing out all this sulfur dioxide and nitrous oxide and so on and so forth, those are also going to have an impact on the person. Therefore, it's not just going to be his smoking habit, it's also going to be the effect of this environment that's going to let him be kind of a more likely to catch cancer. What we have to do here is, therefore, we got to worry about combining, not just using just not one factor in my experiment, but also incorporating other factors also. Those that are also speculated to be affecting the process. That also would be there. So correlation is something that is quite easy to see for us. For example, we see a correlation here, and this is just defined here. That correlation is something that we find to occur together, find to be occurring together. For example, number of packs of cigarettes smoked versus the extent of cancer contraction. These seem to be correlated. But of course, something I should caution you about. Just simply observing a correlation does not really mean that one is causing the other. Just simply because I've got some data and I plotted the data and I see this curvy kind of thing going up, and I see them kind of going up together. This by itself is not the proof that the cause is affecting the effect, and causes has anything to do with the output. The correlation relationship is not really the guarantee that one is causing the other. Therefore, what we have to do is, when we manipulate the input, we then have to observe the output. And we have to really see then, after I manipulate the input variable, does that produce a corresponding change in the output? This is an experiment. This is not passive observation. This is not passive observation. Here we are deliberately manipulating a factor, an experimental factor, and then corresponding to each of those settings, I'm observing the output. Then if I see a dependency, then I'll say perhaps this is causing that. And this again, I have to see in the background of noise that is there, because noise is also affecting the output. Therefore, what we have to say is, it's just like my voice. If my voice was so low or the noise was so high in the room that you could not hear my voice, perhaps I'll be saying. And what you have to do is, you have to make sure the signal is stronger than the noise. Only then you say that the signal really is significant. Otherwise, it is not. So correlation by itself is not a sign for causality. For that, you've got to conduct some special experiments. What kind of factors are we talking about? Of course, there is something called the independent variables. These are factors that we manipulate in an experiment. And the dependent variable is the response. Control variables are those things that you might like to hold constant when a process is running. And random variables are those factors that you're not controlling and no one is manipulating them, and they're changing on their own. For example, vibration and voltage fluctuation and so on. Those might be changing on their own, for example. And of course, something that is called a confounding variable is, I've got one factor already set at a certain level in a particular experiment, and I'm putting another factor in fact coinciding with the position of the first factor. We should try to avoid such settings in experiments, because then it will be very difficult for us to say whether the effect was due to my left hand or was it due to the right hand. This is something we should try not to get into. If we do that, our experimental design would not be a satisfactory design. What is a noisy experiment? On the x-axis, I've got different experimental conditions. A person is given no drugs, or is given just sugar pills, or is given cocaine in an experimental setup. On the y-axis, I've got his heart rate. I measure his heart rate. And notice here there are these dark green blocks, and there are these dark green blocks in each of those settings there. But also there are these light green blocks. What I really observe is not only the effect of this dark box, but I observe this one. So in fact, when I'm watching from this side, I'll say 90 for this response, I'll say maybe 80 for this response, and probably 95 for that response there. Now, what is the problem here? My experimental factors are these: drug, no drug for example, or sugar pill or cocaine. These are my experimental factor settings. Unfortunately, while these experiments are going on, the background is highly noisy. For example, if it's a matter of heart rate, perhaps the person, when he takes these medicines, these conditions, he ingests these things, perhaps at the same time he's also doing a treadmill run, for example, or he's jogging outside or something like that. I've given him this pill and he's gone out, he started jogging. Now the effect on his heart rate is going to be not only due to this pill that I've given him, if at all there is an effect of it, but also due to jogging, or due to his kind of running on a treadmill, for example. Such a background is a noisy background. If I'm trying to see an effect, and that same effect is produced possibly by a noise factor, I've not really designed my experimental conditions very well. What is the choice? Well, just control noise. Look at this condition. Look at this experimental setup. This is a well-designed setup. What have we got there? I've got here no drug situation, sugar pill and cocaine, but I've controlled background noise very well. The result is that I'm able to see, indeed, cocaine causes the maximum rise in heart rate. Sugar pill does not do that much, maybe it does just a slight bit. And no drugs, of course, has hardly anything. It is just the resting time, whatever it is. So this is not a noisy background, and I'm able to see that. The lesson from this is, when you're trying to conduct experiments, don't run the experiments under these conditions. Try to arrange your experimental conditions in such a way that you end up with results that are like this. Except in a case, and except in a very special case, when you want noise also part of your experimental study. And I'm going to give you an example of that when I tell you about the design of chocolate bars. Chocolate bars are pretty fancy things to design. And when I design the, when I talk about the design of chocolate bars, you'll actually see sometimes we'd like to have noise also included when I'm doing a design study. When I'm doing, for example, some experiments, I may include noise. That we'll come back to in a little while. So in fact, what we've figured out so far is we've got multifactorial situations that we must manipulate, and typically we'll be manipulating more than one variable. That's what we'll be doing. We may change more than one factor. We may have their distinct settings there. For data analysis, we'll be using ANOVA. That is something that we'll be doing. Our ultimate goal is going to be to try to construct some sort of a response surface so that we can come back and find the optimum settings for the experiment. Without doing that, we of course cannot really say that we have really helped the process. Let's take an example. Let's take a very simple example. This is an example that's a Six Sigma case. And the problem was this, that many customers who bought Nissan cars, they found after a while that the logo fell off. And you notice the logo there? The logo is right there. That logo is stuck with some pressure and some glue. The logo is stuck on the back of the car. This little sedan there, it's stuck right there. And this logo would keep falling off. And this was a kind of a somewhat of a mysterious situation. People didn't quite know what was going on, and they did want to kind of, do something about it. Now, one way would be to just basically try different glues, or different weights of logos or different sizes of logos, and you basically manipulate only one factor at a time. You could do that. But would that really work? Suppose I change the logo and also I change glue. What would happen? For this, I needed to manipulate 2 or 3 or 4 or 5 factors together. And that is shown in the matrix which is here. This is a matrix that actually gives you an idea of the different factors that might be affecting that logo there. So let's just for a minute, let's draw a little cause and effect diagram. I have on this plate here, I've got logo falling off. Logo falls off. That is the effect. And what are the different factors that might be causing this? I'm again going to speculate. I do not know for sure. It could be glue. It could be the size of the logo. It could be the thickness of the logo. It could be the pressure that I apply. Any of these things, and there may be many other factors also, those might be affecting this thing. If I look at this situation, since any of these and perhaps their interaction might be causing this problem there, what we have to really do is we have to conduct an experiment. And for that we come back to the slide again, and notice here I've got these variables. Addition area, the area over which you apply the glue, type of glue that I use, thickness of the foam styrene which is there between the card and the logo, because the logo is a metal, you don't want to damage the card, thickness of the logo itself, amount of pressure that I apply in trying to make sure I stick the logo firmly enough, and I let it dry, let it set, then I remove my hand there. The amount of pressure that I apply, pressure application time that I just mentioned, and any kind of primer that you apply on the surface of the shiny card which is there. That shine itself, that polymer that is there, that itself might resist sort of proper gluing. So that also is something that I might like to manipulate. Now I'd like to run a simple experiment. And what is the kind of experiment I'm going to run? I'm going to pretend that there are two areas available, 15 centimeter square and 20 centimeter square. Type of glue, acrylic glue and urethane glue. These two types of glues are available to me. Thickness of the foam, it could be thick or thin. The thickness of the logo, it also could be thick or thin. Amount of pressure could be short or long, small and big, and so on and so forth. Notice each of these factors have now what we call treatments, two treatments for each of these factors. So if you now look at the experiment that was run, what experts suggested that instead of trying all 7 factors, we should focus perhaps on the first 4, and they seem to be the ones that could be the culprit, that could really fix the problem. So for that, the first 4 factors were chosen: addition, glue type, thickness of the foam, and thickness of the logo. Having done this, these settings, they were taken out and they were put into a matrix. And notice the matrix there. This is the matrix. This is the matrix. This matrix has these factors there: factor A, factor B, factor C, and factor D. And those are written up here. A represents addition area, B represents glue, C represents the thickness of the styrene foam that is there, and D represents the thickness of the logo. And that is what I've got allotted there. I've got column A, I got here A there assigned, then B assigned on the third column, and then I've got C assigned and D assigned. Now the first trial that I'll be running, I'll be probably mounting maybe 10 of these logos under conditions which is like A at plus setting, which is the high setting, B at plus setting, there is a high setting for it, C at plus setting, and D at minus setting. And I run this trial and I measure the gluing strength, measure the strength with which I can now remove that strength that is there. I have to apply some force to take it off. I do the curing and then I try to take the thing off, and I measure the strength that is required, force that is required in trying to take the logo off. That would have something to do with the lasting quality of that logo sticking on the back of the car. I do the same thing there. So gluing strength is actually the response, and these are the manipulated variables. In my second trial, I do A at high level, B at high level, C at low level, D at low level, and so on and so forth. So I run 8 different trials. And I observed the gluing strength for each of these things. I've got for each trial, I've measured my glue strength. Notice here a couple of things. This is a planned experiment. I have 4 factors that I'm playing with. I have 2 settings for each factor. So I've got 2 to the power 4. In fact, I've got now 2 times 2, which is 4, times 2, which is 8 now. In fact, I've got 8 trials here, but I'm manipulating 4 factors. And I've done a very special construction of the matrix. This matrix has been specially constructed. I'll show you later how you pick the right kind of matrix to be able to do it. Once I've done that, I can run my trials and I made my observation. And this is like that green fat arrow that was there, that was bringing data. So I've got my data now, which is in the last column. My data is right here. My data is in the last column there. I take this data and I do some calculation. Those calculations basically show me the effect of changing A from low setting to high setting, and look at the impact. Gluing strength changes. I do the same thing for B, I do the same thing for C, I do the same thing for D. These calculations have been done in a special way by starting with these input conditions and by looking at the construction of the matrix, the structure of the matrix. Once I've done that, I am able to calculate, generally I'm able to calculate these factor effects there. Now what this is showing is, when I change from plus to minus, these are like 2 settings for A, gluing strength changes. It has this impact on gluing strength. If I plot it up, the plotting goes like this. A is going from high to low in this particular case, and the effect is that my gluing strength goes up. When I change B, this is the effect. When I change C, this is the effect. When I change D, this is the effect. Now by doing those 8 trials, I conducted exactly 8 trials, and 8 is like this. With those 8 trials, I've been able to study 4 factors, and each of those 4 factors, they were set at 2 levels, and my data manipulation technique, my data calculation technique led to these plots that you see there. What does this tell us? Well, as far as this gluing process is concerned, addition area is the one that is really the culprit. Perhaps we were not using sufficient addition area. The other factors seem to have an effect that is more or less flat. So I need not really worry much about manipulating those other factors there. If we really want to, we could actually take them to the level where they gave us, they would give us a higher strength. That we could do. But as far as fixing the process is concerned, if we would change the setting of A from minus to plus, it would immediately give us a big jump in gluing strength. This came out as the result of doing the experiment, and the red circles that show us the optimum settings now for basically running the process, which is there. What are the steps in conducting the experiment? Let's take a look at how we conducted the experiment. We stated the objective. Then we also selected the response. Then we selected the factors that we wanted to manipulate. We chose the factor levels for each of these factors, the X factors. We selected the experimental design, which is the matrix I've been talking about. Then we ran the experiments in a randomized order and we collected the data. Then we analyzed the data and we got those plots done, and we drew some conclusion. And of course, once I come up with an empirical conclusion, I still have to conduct what we call the confirmation run. I have to conduct one experiment under optimum condition. So for example, for the gluing experiment, I should run one experiment that sets A at minus, B at minus, C at plus, and D at plus. I must run one trial to basically confirm what we have deducted, basically, what we deduced empirically. That's something that we got to be able to do. What are the advantages of doing it this way? A lot of advantages. I could produce a lot of information by conducting the experiment. This is like something that I was able to do without too much trouble. I could obtain the main effects. I could also work out the secondary effect, if there is any secondary effect. I could also calculate the interaction effect. Now this could be done for each of the factors that are being manipulated. And in fact, it turns out, because the matrix are very simple to use and the settings are all clearly laid out in the matrix, So anyone who really understands how to manipulate the variables, he can take one of those matrices and run the trials. So running the trials does not really require you to know a lot of statistics. That's something very easy in modern experiments. In the older experiments, you also had to do something called ANOVA, analysis of variance, to come up with your optimum settings and so on and so forth. Now you don't have to do that. You don't have to really worry too much about significance. If you control the background noise, and if you use a simple enough matrix, you should be able to work out the factor effects and their interaction. That you should be able to do. And this is far more useful than one factor at a time experiments, which we are going to see again as we go later on. And later on, as we go deeper into this topic, you'll be able to see that DOE produces information that is substantially better than the information that I would produce by running one factor at a time. For one thing, something that the one factor time experiment will not be able to tell you is whether there are effects between, whether there are interaction between two factors that can be manipulated independently. Their effects might interact in some complex way, and this would not come out if I'd conduct one factor at a time experiment. That's like something that we got to be able to keep in mind. And DOE is also a proactive tool. This is something that I can do in R&D. I need not really go out and wait for production to begin, and the real plant is running there and I start my experiments there, my development work there. That is actually not necessary. That's actually not necessary. I could basically run all these experiments right at the R&D, and really there would not be much trouble at all. So other advantages are also there for doing DOE. It can identify the critical precision parameters to control a process and to improve it. In fact, we saw that factor A was the most significant one. The others did not really matter as far as fixing that the Dodson problem was concerned. That we could see quite easily. New product development, when you're manipulating many different variables, DOE is a shortcut way. DOE is an efficient way, and it identifies the correct levels to help maximize performance and also to reduce defects and the overall cost. That also can be done if we set up those as objectives of the experiment. I am able to do those quite easily. DOE does something even more. DOE does robust design. DOE helps us do robust design. And this is the method that was used by Taguchi. And in that connection, I'm going to again bring back the chocolate bars. I'm going to tell you exactly how to construct a robust design. That's robust chocolate. And that property I'm going to keep a little secret right now till I start discussing Taguchi methods. That I'll do. And the factorial experiments there turn out to be most economical, and they are also very precise. So there are a lot of advantages there. And then of course there are many different techniques, and one of the popular techniques for doing experiments is to use the full factorial design. This is the most complete technique. It can find the main effects and also it can find interactions. So both of those things can be found if you use full factorial designs. All combinations of the different treatment levels, those can be found by doing the full factorial trials. That is there. But if these experiments become too many, I have to use some other method which is called running a fractional factorial run, and that I'll show you. Once we get into that, I'll show you how we come back from full factorial design to a partial factorial design. And that's actually a pretty efficient way to find a lot of information without having to run all the different 2 to the power k experiments, which is like the full factorial design. We'll continue with our lecture in just a little while. Thank you very much.